So the last topic of the class has to do with the models for binary outcomes. And so, this is a topic by itself, but also you will see that one of the models that we use for binary outcomes is a model based in the maximum likelihood estimation. So we use this topic also to consider an application of maximum likelihood estimation procedures. So when we're talking about models for binary outcomes, what we're referring to is where our dependent variable in our model can take two values, a value of 1 and a 0, and where 1 represents success or failure, so of course, 1 is going to be success and 0 is going to be failure. Other examples, it could be, presence or absence. For example, of a disease. So 1 could be a disease and 0 could be the absence of the disease. 1 and 0, for example, can also be used to model participation and no participation, and so on and so forth. So these are examples of of binary outcomes. Sometimes in the literature, instead of calling models for binary outcomes, sometimes they are called qualitative outcomes with two options. Other name that it takes in the literature, qualitative outcomes. Yes, they are called qualitative outcomes with two options. Sometimes they are called discrete dependent variables. Okay, so they can take several names. Now the example that I'm going to be using here comes from a paper by Tom Moraz, where he was trying to model the factors affecting female labor participation. So this is data from 1975. So INLF, so that's in the labor force, which is equal to 0 if it's in the labor force, and which is equal to 1 if in the labor force, and 0 otherwise. And there were several factors that were considered. So the objective was to look at what's the effect of these factors on female labor participation in the labor market. The explanatory variables considered were non-labor income, education, years of schooling, experience, also experience square, age of the individual, and also if the females have kids, so it was the number of kids under 6 years, and also the number of kids from 6 to 18 years. So that's kind of like the data, the broad context of the problem. So this is the binary outcome, in the labor force. That's an example. Summary statistics, the mean. So this is a binary variable, a dummy variable, the mean, 0.58. So remember that represents the proportion. So that's the proportion of females in the labor market. So that means that 56.84% of females are in the labor market. And then we have these other variables. Non-labor income, the average $20,000, average education 12 years, average experience 10 years, average age 42. The number of kids, the average 0.23 that are less than 6 years, so it can go from 0 to 6, and kids between and the number of kids between 6 and 18, average 1.35, but it's between 0 and 8. Okay, so that's kind of the context. Okay, so let's talk a little bit about the theory. So remember here we have y is equal to 1 if the individual is in the labor force, and y is equal to 0 if it's not in the labor force. The first model that we can use is something that it's called the linear probability model. But before we get to that, let's talk about the probability distribution of these binary variables, of these variables. So we're going to be looking at two models. One is going to be the linear probability model, and the other one are going to be models based on maximal likelihood estimation. And the first one is going to be just like an OLS procedure. So yeah, let's talk about the theory. Y equal to 1 if the individual is in the labor force, 0 if it's not in the labor force. For this type of outcomes, Y is said to follow a Bernoulli distribution. Okay, or this is the probability density function, is what's called the Bernoulli distribution. So let's look what is the PDF, this Bernoulli PDF for a specific observation I. So f of y is the PDF, can be written as pi to the yi, 1 minus pi to the 1 minus yi, and yi can be, take the value of 0 or 1. So this is the probability density function. The mean of this function is that probability pi, and the variance is pi times 1 minus pi. Okay, so probability density function is a function. Of the variable that we're interested in analyzing. In our case, the variable is y. So let's look at an example to see how that works. This Bernoulli distribution, the classical example is to model the outcomes of tossing a coin. So let's say if head is equal to 0, so that's the value of y, and tail is equal to 1, so the variable is y. So for this process, the specific values for the probability density function is if the pi is going to be to 0.5 if it's a fair coin. So yi 1 minus 0.5 to the 1 minus yi. So if we want to calculate what's the value of the probability density function for y equal to 0, that should be equal to 0.5 to the 0 times 1 minus 0.5 to the 1, and that should give us 0.5. And follow the same logic, it can be shown that f to the 1, so that the value of the probability density function when y is equal to 1 is also 0.5. Okay? So as you can see here, in this model, the way that we're considering pi is like a parameter, a coefficient. So we're saying the expected value of yi is equal to pi. But if we want to see how is that this outcome is affected by some explanatory variables, what we can do is we can make this probability function, the probability pi, we can make it a function of explanatory variables. So we can write pi, which is the probability that yi is equal to 1 conditional on xi, and we can make it a function. We can make it a linear function of the coefficients. Okay, and we know that by this definition, the probability that y is equal to 1 is actually the same as the expected value of yi conditional on xi. Okay, so that's a key think in this model that the probability that y is equal to 1, is equal to the average of the expected value of yi conditional on xi. So how can we go about estimating a model to explore the effect of explanatory variables on pi? So I already mentioned that the first thing is we can use a linear probability model. So in the linear probability model is nothing else but our old friend, the linear regression model. And so remember that since the expected value of yi conditional on xi for this model is going to be x prime beta, and that we know by the definition, you see the expected value of yi conditional on xi is the same as the probability that I is equal to 1 conditional on xi. We can use this definition for the interpretation of the coefficients of our linear regression model. Okay, so this is very important, to remember. Remember, so this first part is what we've been doing, but knowing that the expected value of yi conditional on xi is equal to the probability that yi is equal to 1 conditional in xi is what is going to allow us to interpret the coefficients of the linear regression model, which is called the linear probability model, in a correct manner. So those, using the OLS, we will use yi as a dependent variable, which can only take values of zeros and ones. So if we have OLS as a dependent variable, and of course the x's as the explanatory variable, then the results is going to provide us with estimates of the effects of the explanatory variables on the probability that yi is equal to 1. Okay, so probably this sounds more complicated than it is. So let's look at our example. So what we have here, and unfortunately I don't have SAS here in my in this laptop, but I'm going to show you the SAS code. So we imported the data, we deleted missing observations. I already calculated the proc means. And that's kind of what I already showed you before. We have 753 observations. I think that 3 were missing observations, so we get rid of those since we don't have values for the dependent variable. And then, for the linear probability model, it's just like a linear model where we have in the labor 4, so zeros and ones as the dependent variable and then as the explanatory variable. So you are familiar with everything. I'm using Y heteroscedastic consistence covariance metrics, and I'm also getting the predicted values for y hat in a file that I'm calling it labor2. Okay, and then I'm going to be predicting the observed values of the dependent variable and also the predicted values. So let's look at that. So that's kind of just part of the linear probability model. The linear probability model again is just like an OLS using our binary outcome as the dependent variable, and we have the other set of explanatory variables. So this is the regular output of a linear regression model. The statistics, so the model is significant. The R square 0.25, and now we have these coefficients of the model. And what we have here is very straightforward. So let's see how do we go about interpreting these coefficients using those ideas that we discussed previously. So remember here, we got this 0.03 39. So remember, so this is the effect of an additional year of education on the average value of y. But since the average value of y, remember here y can only take a value of 0 and 1. So it's easier to think again in terms of that the expected value of y conditional on xi is equal to the probability that yi is equal to 1 conditional on x. So using that idea, then the way to interpret this coefficient. So we said that each additional year of education increases the probability of female labor participation by approximately 4%. Again, so here the trick is that, the way to interpret is the effect on the probability that y is equal to 1, which in this case is the probability of female labor participation. With experience, we can do the same thing. Each additional year of experience will increase the probability of female labor participation by about 2%. In terms of the relative importance of the coefficients, you see the one that has a very large effect is this, the number of kids that are less than 6 years in the household. So you see each additional kid that it's whose age is less than 6 years decreases the probability of female labor participation by about 27%. So that's a very, very large effect. Okay, so in short, the linear probability model for binary outcomes basically is a regular least squares regression model. And for interpretations, we need to remember that the effect of the variables are the effect on the probability that the dependent variable takes the value of 1. Other than that, it's very straightforward. So, it sounds pretty easy. So some of you probably are wondering, okay, that sounds pretty easy. Then, maybe there is a catch. Of course, this linear probability model is going to have some limitations, that you need to be aware of. And the limitations, are related to, the first thing is that the errors are going to be heteroscedastic. So, you need to use feasible general least square or the White heteroscedastic consistence covariance metric. So what's going on here? So you could use the feasible general least squares, because remember that by definition, the variance over the errors are going to be xi prime beta times 1 minus xi prime beta, and that comes from the fact that, remember, yi is a binary outcome. That's the probabilities are pi 1 minus 1 pi. Remember, that was the variance of the errors, which is the same as the variance of yi conditional on xi. Okay? So be aware of that. The other problem is that the predictions of the model can be higher than 1 or lower than 2, which are not valid probability values. And again, here I don't have the outcome, but I have coded. You can do it. I'll send you the data set. You can code this one. When you print these observations, you will see that some of these, the y hats, some y hats are definitely higher than 1. And you could potentially have some y hats that are also lower than 0, which in terms of probability, doesn't make any sense. So that can be problematic. And the other, limitation is that, remember here you know that yi is a discrete variable, and you know the true functional form for pi. So you lose efficiency if if you are sure, if you know the true probability density function for pi. Okay, so you can get, so if you use this additional information about the specific probability function for well, it should be the probability density function for yi, not for pi. For yi, potentially you can get some efficiency. I mean, if you add this additional information. Okay, so if that's the case, so now let's look at the second option. Okay, so let's see what else what other models can we consider. Well, if we want to obtain predictions of the probabilities within 0-1 interval, what we could do is, remember, the problem is that before the model for pi that we consider was xi prime beta, but that doesn't ensure, there is nothing here that is going to ensure that this probability is going to be between 0 and 1. So, we can use a continuous probability distribution for pi, and then also the maximum likelihood estimation procedure for estimation. So here, so what happens, when we, with the Probit model? Basically, the Probit model, what we're doing is that we're assuming that pi, to remember, is the probability that yi is equal to 1 conditional on xi, is given by the cumulative standard or the standard normal cumulative density function, which is more complicated if we write it this way. So that's the standard normal probability density function. Evaluated from -infinity to x I prime beta. So, I don't know if you're kind of confused about these things. So remember, these are just functions. These two are functions. They look kind of complicated. So this is the standard normal cumulative density function. Let me see. Standard normal cumulative density function. So sometimes they call it, this is the CDF. Okay. And this is the standard normal. So this is the probability density function, or PDF. Again, these formulas look complicated, but the standard probability density function, I'm going to write it here, of t. So this is the evaluated at t. So we have here, so this is a probability density function for a normal distribution. Exp minus 1/2 t minus mu squared over sigma squared. And to define the standard normal, sigma squared has to be equal to 1 and mu is equal to 0. Okay, so that's kind of the standard normal probability density function. So what we're doing here is, we're taking the integral. In this part, what we're doing is we're taking the integral of this function from -infinity to xi prime beta, and that's kind of denoted by this expression. So, kind of, graphically, what's going here, so remember, that the PDF looks like that. So what we're doing here is we're calculating the probability from minus infinity to x prime beta. That's basically what you are doing in that expression. So you are calculating a probability. So by using this function, what you are doing is ensures that this product x prime, xi prime beta, since the probability can only be between 0 and 1, so you ensure that the value that you obtain there is between 0 and 1. So we could also use the logistic distribution, and if we do that for pi, and we get what's called the logit model. So that's xi prime beta divided by 1 minus xi prime beta. Okay? So this is the basis. Again, another way to think about this model is what we're trying to do is, we're trying to come up with an expression for the probability that yi is equal to 1. Okay, and we have these two options. Actually, we could use other options, but these are the most popular ones. So what about estimation? Well, we could use FML. So remember, going back to our previous class, so here things change slightly a little bit because now we have a conditional distribution. So here the probability density function of yi conditional on xi beta is equal. So remember, this is the Bernoulli distribution. Remember, before we called this thing pi to the yi, but now we have a specific function for pi times 1 minus the CDF evaluated at x prime beta to the 1 minus yi. So this is the PDF. Remember, in the way that we wrote it before was 1 minus pi to the 1 minus yi. So remember, for MLE, you always start with the probability density function. And then we can write, we already know this thing, we can write our likelihood function. So we can write our likelihood function. So it's going to be the betas as a function of y's and a matrix X, because it's a function of all the values for yi and all the values for xi. And remember, that's just like a product of those individual probability density functions. It's very standard, so just basically we have to copy that, and we know that's a multiplication. 1 minus theta 1 minus yi. Okay, so that's our likelihood function, and then we can find our log likelihood function. Beta conditional on y till the next, those are all the values of y and all the values of x. So if we take the log of this expression, the natural log, so that's going to be equal to the sum of yi times the natural log of the standard normal CDF evaluated at those values plus 1 minus yi times the natural log of 1 minus, again, the standard normal cumulative density function. And we have our log likelihood function. Now, the previous example that we had is very simple. Here what we need to do, to be able to maximize this function, remember we had to take the derivative of the log likelihood function with respect to beta and make it equal to 0. as we did before. I don't know what I'm touching here. This thing make it jump. But there is not a closed form solution, like in the example simple example that we look at when we're talking about the theory of maximum likelihood estimation. So, numerical methods are needed for estimation, and that's kind of like what a software does for you. So how do we go about estimating this? So, it's already coded. So there is QLim procedure. It's qualitative limited variables in SAS. The way that we write the model is the same as before. Here we have to specify the discrete, and we write normal for the Probit model. So here, we're also going to requesting the output to have the marginal effects, and I'll talk about that in a second, but I just want to be complete. And the file where that's going to be saved is going to be called outqlim, and this outqlim is going to include the original data plus these marginal effects. Okay, so if we do that, remember we're trying to estimate these beta hats. Well, those are going to be the ones that we're estimating. So we get the results. Let me see if I have them here. The results. We have to go back. So these are the results. So QLim procedure, value 0, 1. So have in mind that the index here 2 is for like the y equal to 1. Have that in mind. We'll go back to that later on. But endogenous variables, we only have one, so that's our dependent variable. The name, and so these are optimization procedures. So it took 13 iterations. This is the log likelihood value. And these are names, and we don't need to talk about those things. We'll go back to this goodness of fit measures, but the log likelihood value 406. Previously, remember, we talked about the likelihood ratio test. We'll go back to that one. That's kind of a result. So this likelihood ratio test is going to be important in this case. So you check also to see if the algorithm converge. And then, we have the parameter estimates. Okay, so what are these parameter estimates that we get? So remember, these are the betas from that cumulative density function x prime beta. So these are those betas. Okay, those betas that are inside. It's going to be beta naught hat, beta 1 hat, and so on and so forth. Okay, so how is that we go about interpreting those results? Well, you have to be a little bit careful because those betas, so this is a linear model, and the idea generally, when you are estimating linear models, the parameters do not have a very straightforward and direct interpretation. Usually are more interested in marginal effects rather than the coefficients. So remember this beta case here, only have interpretation. Now, okay, most of the time they don't have an interpretation. The only thing that you interpret is the sign and the significant. So of course, if it's positive, the sign, we know that the corresponding, if the beta k is positive, the corresponding xik variable has a positive effect on the probability that yi is equal to 1, and if it's negative, of course we know that that variable has a negative effect on the probability that y is equal to 1. Okay, but the betas by itself don't have an interpretation. Now, once in a while, if you are estimating some sort of a structural economic model, assuming that those coefficients correspond to the parameters of an indirect utility function. There is some discrete choice models where you can assume that those coefficients have are defects on the indirect utility function, but most of the time it's only the sign and the significant can be interpreted as defect on the probability, but the actual value doesn't have a direct interpretation. Okay, going back to our results, basically what we will say, if you remember education, we find that it has a positive and significant effect, which is consistent with our linear probability model. Experience, positive and significant, and remember the number of kids, negative and significant. So that means that the more younger kids that you have, the lower the probability of participating in the job market. But by itself, those values, don't have a very meaningful interpretation. So again, what we're interested in most of the time is in calculating marginal effects. So let's look at the theory for that. To calculate marginal effects. So remember that here we say that Pi, which we say is the probability that yi is equal to 1 conditional on xi, is equal to the expected value of yi conditional on xi for this model. And this, in the Probit model, we have the cumulative density function evaluated at xi prime beta. So for interpretation, what we need to do is we need to calculate the derivative of the average value of y with respect to xi, which is the same as the derivative on that function, cumulative density function, with respect to xi. And that is, so remember, this is the CDF evaluated at xi prime beta. So this is going to be the PDF, the normal PDF evaluated at xi prime beta times beta. And there are going to be two options. So this is the idea. So remember that these marginal effects basically depend on the specific value of xi. With nonlinear models, that's the case. If you want to calculate a marginal effect, the value of the marginal effect is going to change from point to point. Just to digress a little bit, so remember, if you have this function and the relationship between y and x is that, remember that if you have a nonlinear model, these slopes change from point to point. So to calculate marginal effects, you need to calculate them at a specific point. So in economics, most of the time what we do is we calculate the marginal effects at the average. So we can calculate that marginal effect at the average value of the x's. But in this context, there is the alternative of calculating the average of the marginal effects for each xi. Oh, I ran out of space. So both procedures asymptotically are supposed to be equivalent. So the other marginal effect, so what you do is you calculate the marginal effects, the average of those marginal effects, for each xi prime, and that's what's called sometimes the averaging partial effect. So remember, intuitively here you have the marginal effect, so the effect of the variables at the average value of the explanatory variables, and here this is the average of the marginal effects for all the individuals. So they are both acceptable. The ones I'm going to show you how to do here in SAS are these ones. But if you use something like Stata, it's actually easier to calculate these things. If you wanted to calculate the marginal effect at the average in SAS, it's possible, but you probably need to use ProcIML. so things get a little bit complicated. Okay, so this is what we do here. So in terms of coding, that's what I was telling you. So if you have this proqlim, you request the marginals, and you save that in this file. And what I'm doing here is I'm calculating the means of that file where I store all the marginal effects. And so is the average of, in this case, we have 753 observations, so it's going to be the average of 753 marginal effects. So here, remember, and this is kind of, I was telling you that this is a little bit kind of confusing because of the way that SAS does. So let's look at the effect of education. Let me see. So let's go back to what. So the value of 2 yes, so the things here kind of are reverse. So let's see for education, the ones that we had used before as an example. Remember, so, I mean, that's a problem, they changed the index. So remember that what we call, so what we call previously 1, they changed it to 2, and what we call 0, they change it to 1. So you have to be a little bit careful. So let's focus on this one. And this is kind of always kind of confuses me too. Okay. And where did I get that information? Remember, I had mentioned this here before. So, I mean, if it's a 1, the index 1, it's for original value of 0. And if it's 2, it's for original value of 1. So this value here, 0.04. Remember, all of these values represent the sum of these marginal effects. Okay, for the specific variable that we're analyzing. So this is the first variable. Let me go back to the model. So the first variable, the second variable, 3, 4, 5, 6, and this is our beta naught. So beta 1, beta 2. And so on and so forth. So let's look at education, which is beta 2. So this coefficient is going to take this derivative times beta 2 over n. So beta is the vector of all the coefficients, and beta 2 is the specific coefficient, for the specific variable that we're interested in. So we're interested in the effect of the probability with respect to education, which, I mean, we call it x2, and we're finding that average 0.041. Okay, so we can say that each additional year of education increases the probability of participation. The probability of female participation in the labor market by it should be 4.1%. Okay, so that's kind of like the way that we interpret. That means a marginal effect. Again, for experience, let me see the other one that we looked before. Remember that this was for each additional, young children. Before the probability was 0.27, now it's about 0.27. So it's kind of the same thing. Okay, so we have that. Now here, what I've done is, I have the marginal effects. Remember that we got from the linear probability model where we chose the coefficients. And these are the Probit model, which kind of, involve this kind of complicated calculation. So involve that complicated calculation. If you see, actually, they are not that different. The effect of an additional year of education was 0.039 in the linear probability model and 0.04 in the Probit model. Experience very close. Additional number of kids is the same. So, again, the linear probability model is a simpler model. And sometimes, but that's the problem. It's not always. It's going to generate results that are very similar. Most of the time, they're going to be similar. I mean, that kind of has been my experience. Now, there is this situation where you have two groups, usually of researchers, some that really like the linear probability model and the others that just hate it. And some researchers like it because, the linear probability model is a linear model. So basically, if you are, for example, have problems with endogeneity or issues, which is, happens all the time, then you can use a linear probability model, and then you can use all the theory that we had talked about before, regarding endogeneity. You can use two-stage least squares, and so on and so forth. Dealing with endogeneity in nonlinear models, like the Probit model, is generally is a little bit more difficult. Or, if you are talking about panel data models, again, linear probability models are easier to deal with. You use probability models. I mean, there are some complications in that context. Okay, so let me see. So what else? So let's go back. I guess some things that I haven't talked about. So we have that. I discussed the coefficients. I talk about this likelihood ratio. So this is kind of important test. If you are trying to evaluate the goodness of fit of the model. Remember, in the linear regression model, we have the F statistic, and then we have the R square. So that's kind of what you have here. Yeah, so let's discuss those things a little bit and see if we understand some of that output there. So for goodness of fit, there are multiple options, but it's always recommended to report first the likelihood ratio test for the overall significance of the explanatory variables. And then, the null hypothesis is that, none of the variables helps you to explain that probability, and the alternative that, at least one of them is used for helping you to predict the probability that y is equal to 1. So this is a likelihood ratio test. So remember, this is going to be given by 2 times the log likelihood value of the so let me see, it's going to be the unrestricted model versus the restricted, or the other way around. So let me see. So you have the restricted minus the log, well, and I'm going to write it the way that they have it written here. So you have this 2 times the log, the restricted minus the unrestricted. And remember, that's supposed to follow a chi-square distribution with the number of explanatory variables k, I'm going to write k, that's the number of explanatory variables that you have in the model. Okay? So, if you reject that null hypothesis, then that means that the model is useful for prediction. If you fail to reject the null hypothesis, basically that means that, none of the explanatory variables are good predictors. And I'll have to go back to this expression here, but I don't remember. So, we will double check. I mean, the good thing is that SAS is going to give us this value already. And the only thing is we're going to have to go to the chi-square distribution at a given level of significance to see the critical value. Okay, so it's very straightforward. So let's go back to our example, because there a sign that sometimes they change. So from the top of my head, so you see that's the value that we have for the likelihood ratio test. And you can go to a chi-square table, let's say at 5 level of significance. So here we have 6 explanatory variables. 1, 2, 3, 4, 5, 6. So if you can go and check 6. So the critical value is 12.5. Okay, so since um, 217.31 is higher than 12.5. We reject the null hypothesis, and and basically there's evidence there's evidence that the x's have explanatory variable. There is evidence that explanatory variables help to explain the probability that yi is equal to 1. And that's also another way to say, you see, that's evidence in favor of the unrestricted model, which is a model with explanatory variables. Okay. So, and usually that's, you have to report that. It's good to report the value, and sometimes even the p-value at which you reject the variable, to show that the model, that your model is useful for prediction. And the other thing that you are supposed to report okay. The other thing that you're supposed to report is one or several pseudo R-square measures. So here, we don't have, so remember the R-square, what you have in the R-square comes from the least square model, where you are minimizing the sum of square residuals. Here you are not minimizing, you are maximizing. Remember that log likelihood function. So there is not exactly the same type of measure. So, there are a lot of researchers that have come up with these pseudo R-square measures, and then they don't have the same interpretation. So you can always report one or several of them, but SAS basically gives you this very long laundry of pseudo R-square measures. But most of the time, they are really not used, and they are not really interpreted, but you can add one of them. I most of the time the only thing that I report is the likelihood, the log likelihood value, and the result of a likelihood ratio test. But that's kind of what all these researchers have been very creative, trying to come up with these measures of goodness of fit. But they don't have the same interpretation as the traditional R-square, so it can be kind of tricky to present them and even try to interpret them. Most researchers, again, just present the likelihood value and then the results of these likelihood ratio tests. And I think that what I had before, is consistent with this formula. I think that the minus disappear because they switch the order of the restricted and the unrestricted model. And by doing that, you got rid of the -2 that we had when we were talking about the theory. And that's kind of what's causing confusion. But the formula, is exactly the same. Okay, so this is what I have for you regarding the Probit model.